if we go to the tutorials on the Fish Pace Hackweek, we are going to be doing the remote sensing reflectance. So if we go straight to the notebook where the eyeball is, and all right, so you press this orange button for the Jupyter Hub. Come on, come on, come on. Overwrite the file. There we go. Okay. We've tried it on a few. It looks like it seems to be working for everyone. So hopefully that that worked for you as well. I'm so excited about this one. I love remote sensing reflectance. So yeah, welcome to our first sort of science tutorial here. We're going to be getting friendly with hyperspectral remote sensing reflectance. It arguably, might be one of the more challenging aspects of working with PACE data, but I think it's important to kind of address it front and center and demystify the experience, because it's really the foundational product from which all other ocean color products are built. And the goal here is not to turn you into an ocean color algorithm developer, in 30 minutes here. Instead, I want to leave you comfortable opening the data, poking at it, visualizing it, asking good questions of it, having access to more wavelengths of color information has really been a sea change for our community. But it has been challenging for even veterans of the field to emerge from their comfort zones and really embrace the true potential of hyperspectral data. As Jeremy had mentioned yesterday, a lot of the products being offered by PACE right now are sort of the baseline required products, and they may not necessarily be utilizing hyperspectral data. So, all right, so we'll start with the basics. R, R, S. Right off the bat, it's confusing because sequentially it stands for reflectance subscript remote sensing, but we will refer to it as remote sensing reflectance more commonly. So as we covered in the science talks, at the most basic level, this is the fraction of sunlight that hits the ocean, interacts with stuff in the water, phytoplankton, sediments, dissolved organic matter, and then scatters back out of the ocean and up to the satellite. So if there is anything at all optically unique happening within the water, it is contained somewhere within this signal. So this is one of my biases, and I will own this. I do think it's really valuable to spend time with this raw reflectance before jumping straight to products like chlorophyll. Because historically, we've had, maybe 5 to 10 spectral bands to work with, and PACE is just blowing that wide open. We have nearly, 200 wavelength bands across the visible spectrum, which is amazing, and also slightly terrifying, because instead of, one map, now we have a giant stack of maps, and that's where visualization and smart summarization become really important here. So and right off the bat, I realized that I just said I want to shy away from using derived products for now, but owing to the fact that we're mapping out 172 wavelengths of information is not really easy to conceptualize, and because of this, PACE has introduced us to a new indicator that kind of helps us summarize this hyperspectral information called the apparent visible wavelength, or AVW. This is actually bundled together in part of the AOP file. So if you download the AOP level 2 files, the AVW is already computed and calculated in there. But conceptually, AVW answers a pretty simple question. Where is the center of mass of the reflectance spectrum in the visible range? The novel aspect here is that it uses all the reflectance wavelengths to determine its value, not just one or two, as is the case for a lot of other derived products. So the way to interpret this is straightforward. Bluer waters tend to have lower AVW values, that shifting point that you can sort of balance the spectrum on the tip of a pin. It shifts more towards the blue wavelengths. Greener and more optically complex waters shift towards the center or longer wavelengths, and thus they have higher values. So lower values, bluer; higher values, more green to red. It's physically interpretable and kind of visually intuitive metric to help us kind of grasp the hyperspectral information and find patterns that we might want to explore further is kind of the idea. So this is going to be a recurring theme here. We want to summarize strategically so we can explore before kind of going back to the full spectrum. One more thing I want to convey before we get going here. At first glance, using RRS can feel a bit removed from the ecology that we actually care about in fisheries, and that is a fair reaction. But the key thing is, once we jump straight to products like chlorophyll, we're only using a small slice of the spectrum, and we inherit all the assumptions built into that algorithm. Looking at the full reflectance spectrum lets us see all the diagnostic information in the signal without those assumptions. That often reveals sometimes subtler spatial and temporal patterns that are tied directly to ecological change. So anyways, that's my, I'll stand down off of my soapbox. But so what we're going to do today, we're going to download and open a PACE RRS scene level 2 file. We'll look at the structure of the data. Then we'll create a sort of summarized visualization using of the AVW, so we're not drowning in bands. Then we're going to extract some data from that. We're going to draw a little transect and extract some of the reflectance data. And then we'll look at the reflectance data within that transect. It's a little more manageable. And then try to identify some of the patterns that we pick up in the scene here. So what we're not doing is tuning algorithms or arguing about which atmospheric correction is best. Those are great Hackweek conversations, just not in this block here. So, all right, first things first, we're going to go ahead and grab our, let me just make sure that I restart. Not restart. Is it? Yeah, I do want to restart my kernel. You all shouldn't have to, but I had some memory already loaded in here. You should only need 2 gigabytes here. I think I loaded a 2 gigabyte instance, so if it crashes for me, it'll crash for all of you. But I went through, so I don't think that's the case. All right, so we're going to grab our data using the Earth Access tool, which Eli introduced us to yesterday. It handles authentication and the searching and downloading in a way that's reproducible and scriptable here. We're also going to be using X-array here, and if you take nothing else away than this from the tutorial, X-array is really good at handling labeled multidimensional data, which is what we're dealing with here. It gives you, this will end up giving us named dimensions like wavelength and lat and long, which kind of help make the code a little more readable and harder to kind of mess up essentially. All right, so we're putting in our query here using the PACE L2 AOP as the short name. We're just going to grab a single day here in March 5th, 2025, and I put a bounding box in here. So we log in with our Earth data credentials. It's nothing fancy, but it's a very powerful workflow. I want to emphasize too about we're being really explicit about what we ask for: time, space, product, and that's an important part for the reproducibility. In the presentation yesterday, we talked a little bit about the nuances between level 2 and level 3 data, where level 2 data preserves basically the original resolution of the sensor, but the data is served in smaller granules as it goes around the globe instead of one total global file. So the bounding box here just allows us to only grab the files that overlap with that particular box. We're going to spend a good chunk of our time in this class in level 3 space, and we're going to talk about why that is later today. But I wanted to give you an example of dealing with level 2 files since it's organized a little differently. What else did I want to say about that? I'm not sure. Anyway. Oh, I did want to say the bounding box doesn't really work for level 3 files. I just wanted to mention that level 3 files are served up as a global file. So if you put in a bounding box, you can put it in there, but it's just gonna give you the global data file back. So it only works sort of effectively in the level 2 space here. All right, so this variable file set here contains the results of our query. Now we're going to open the data set. Here we go. All right, you notice I opened this data set with chunks here. What this is doing is telling Xarray to use Dask-backed arrays, so the data is loaded lazily instead of all at once. Kind of in practical terms, it means we don't pull the entire data set into memory immediately. We only load the pieces where we actually touch, like when we plot a map or extract the transect. It's a really important aspect of PACE data because even a single day, a single transect, or a single image here can be pretty large, and we don't want to discover our memory limit the hard way here. So chunking is kind of like slicing a big cake. Instead of putting the whole thing on your plate, just grabbing pieces as you need them here. So the file contains groups, some of which contain actual variables of interest, some of which contain latitude and longitude info and so forth. And after we open up the data set, we merge all the groups together. Let's see. Yeah, merge all the groups together here. So anyways, the point of that being that we get reflectance, latitude, longitude, wavelength as sort of one coherent object, and this works because they're all the same dimensions. This is part of the nice part about how netcdf files are arranged here. So they're easily stackable. They're all the same dimensions. Right. So if you print out the data set, you see that this is sort of dimensions. Yeah, the latitude, longitude, wavelength, and the wavelength running across hundreds of over 172 values here. So this unified chunks here, this just makes sure that all the variables in the data set are chunked in a consistent way. So when data come from multiple files or groups, different variables can end up with different chunk layouts. So that it can slow things down or cause warnings when you're trying to operate on them together. So this unified chunks kind of lines everything up. So Xarray and Dask can work effectively under the hood. So yeah, just kind of making sure all the puzzle pieces are cut the same way, before we try to put them together, I guess. All right, so let's get our hands dirty here. I'm going to load up a bunch of libraries that we're going to be using. Right, and we're going to open up some variables in our data sets. I like to work in this space, pull out the RRS and AVW. It is, we're not disconnecting them here, but each of these data arrays still carry their latitude, longitude, and wavelength coordinates with them. They're basically views into the larger data set. But I do like kind of pulling them out just because it's a little easier for me to wrap my mind around. All right, so let's take the AVW product here that we pulled out and plot it up real quick. Just a real quick figure. And it looks horrible. We get the ick here, and it shows us really nothing. Some data sets are better than the others. I think one of the things is that there might be some minimum, maximum information that automatically scales the color bar. That seems to be lacking in this particular file. So we can then kind of clean it up a little bit here. We can adjust the scale so it better represents sort of a histogram of the data. So we'll define our min and max by looking at basically the first and 99th percentile and set those as the min and max there. Kind of better represent the color within the file and get rid of those outliers there. We're also utilizing Python's Cartopi, I don't know if that's how you pronounce it, library, as we set up the plot. We use this a lot. It's really helpful for projecting geographic data. And then we can call this subplot KW or keyword, and it feeds. We feed it a projection as a way to say, when you create these axes, make it a map, and then we can set the axis extent here, and you'll notice that I'm identifying that projection again with CRS, a plate carry projection. Even though the axes are already using a plate carry projection, Cartopi, someone needs to tell me how to say that right. It still needs to be told what coordinate system the numbers I'm passing, are expressed in. So when I call set extent, I add CRS plate query to say, these longitudes and latitude bounds are in geographic coordinates here. Right. Takes a second here. Now, we could save a little memory. I'm actually plotting this entire level 2 file and just setting the axis extent here. We could trim this down and just select this portion, but I think we do that exercise later on, but just to give you an idea. All right, this looks a lot better though. We see gradients and plumes and boundaries between water masses, and suddenly this isn't just numbers anymore. As is, this plot itself doesn't tell you why something looks the way it does, but it might tell you kind of where to ask questions. Since the AVW uses the full hyperspectral signal, it's useful diagnostic to really elucidate some of these patterns. So, all right, let's say an area here grabs our interest. For now, let's just see what happens when we move sort of off the coast of Louisiana, across the shelf and into the deep waters of the Gulf here. Let's see. So let's define. What we're going to do is define a transect, and feel free to modify your own here if you want. I just grabbed basically 29.5 and 93 as the starting lat 1 long 1, and then we're going to end at 27.5 and 92-ish, so around here. So we're just going to do a little diagonal line like that. Yeah, all right, so we're gonna define that transect, and then we'll define a number of points to extract here. You can increase this or decrease it. If you put too many points, the worst that's going to happen is that we're going to replicate samples. Right now we're just exploring, so let's just create that line, put on the image to see where we are. If you want to go across that line, you only want 5 spectra to represent that, or 10, you can do that. I put 200, so we'll get a good amount of representation there. All right, so let's check out where that is. There we go. Went ahead and plotted the transect line right on top of that. Let's see. All right. So before we can look at the spectra, we need to figure out which of those satellite pixels correspond to those lat-long points in our transect. We've defined the transect, but we haven't pulled the data yet. And there's a lot of different ways to extract data along transects. You can interpolate along the path. You can use there are line algorithms as well that may effectively work better, but I like to be able to see how things are happening, and so what we're going to do is basically just extract the nearest neighbors for every lat long that we created in that transect. It's transparent, easy to explain, and kind of good for exploratory analysis. So, we're not interpolating everything. We're just going along that line, and we're grabbing the closest pixels along this path. In reality, that makes the extraction just ever so slightly zigzagged along this line, but let us not fret over things that are not important. We're here, we're essentially subtracting. What we're going to do here is we're going to subtract the lats and longs from basically lats and longs that we defined along the transect from those in our pace file. So we index locations where those values are the lowest, and then the lowest difference is essentially the closest pixel. So with those indices defined, now we can sort of sub-select the data at these locations for the reflectance and AVW. And this is where we kind of try to balance cloud computing versus using just a little memory here. I'm going to go ahead and run this. We're going to use we're using this iSelect portion here to kind of locally load these points, because if we don't, we're going to risk loading in the full data set as we go through each iteration of a loop that we're going to go through next when we grab spectra to make our plot. So we're just gonna grab only those data that go along that transect here to make things a little more easier to handle. Okay, so this might take just a second, but not too bad. All right, so now that we have our transect pixels, we're going to pull out the full spectrum for every single point along that line. That's 172 layers of reflectance at each pixel. To make this a little more intuitive, I love to do this. So we're going to color each individual spectrum that we take out. We're going to match it exactly to the colors in the AVW image. So when you see that transect cross a, sort of yellowish orange pixel, we're going to color that entire spectra the same exact color. So just to make it a little more intuitive and so we can connect it. So to implement this, yeah, we need to pull out all those spectra. And then we're going to just loop through them one at a time because we're going to measure the area under the curve of those spectra to create some useful plots. So we'll kind of get into why that is. So we're going to generate two plots. The first is a raw reflectance spectrum here. So we're pulling out the just to kind of set the stage here. We're defining a color map. I like the jet colors. I'm sorry, it's not colorblind compliant. But it helps with the explanation of AVW here from relative terms. But we're going to normalize the color. So basically setting the color bar such that we defined Vmin and Vmax earlier as being those percentile ranges, and we're basically setting that color bar so the lowest value of the AVW is 0 and the top is 1 essentially, is what it's doing, and that's going to help us when we're sort of plotting the spectra later. So we're going to end up plotting our spectra and also a normalized spectrum here. So the regular spectrum, the remote sensing reflectance, the raw units come in inverse steradians. And the second plot normalizes each spectrum by the area under the curve. All that means is that we take the trapezoidal integration. So it really is just measuring all this area underneath each reflectance curve. And then we take the original spectrum and divide it by that area essentially. And what that does is create these differences in the plot that makes all the spectrum equally bright, essentially. So we can really focus on the shape of each spectrum instead of these differences in overall magnitude. But both plots are telling us something useful here. Here's the fun part. Go back, pick a new transect, and you can see how the spectra change for different areas. But you can really get a sense for how different water masses look just from looking at these sort of spectral fingerprints. So as you can see we pulled this from the transect. There's a lot of sort of difference in optical properties that can produce substantial variability here in the spectral shape over a relatively short distance as we've just kind of crossed over the shelf here. So on the left here, this is the raw remote sensing reflectance, and it is color coded according to our AVW values again. So matching up with our map here. And then on the right, we have we have normalized each of the spectra. So we've removed that effect of overall brightness. Again, it's partly an aesthetic choice, but it also makes it easier to sort of focus on those differences in spectral shape, which are a main thing, driving changes in the water hue or the color. And I do want to mention the way the AVW algorithm works as well. Whether you calculate it on these spectra or the normalized spectra, you get the same exact AVW number. So it does not take magnitude into account. It all kind of cancels out, and you get the same result either way, which is why we're able to do this. Now, tying this back into what we talked about in our previous lecture on the inherent optical properties, or IOPs, all these bumps, wiggles, and the magnitude of these spectra are all controlled by the IOPs in the water. The waters that are closer to shore tend to have more of the CDOM and detrital material, which absorbs a lot of blue light, which is why our sort of orange and red colored spectra here are more nearshore waters show a dip here in sort of the blue portion of the spectrum. Now, water also naturally absorbs a lot of red light. Pure water with nothing in it, it absorbs a crazy amount of red light as well. So in general, when we get a good reflectance signal in the red here, what that means is the light basically didn't get to interact with the water much. It hit the surface and it got backscattered by a bunch of stuff. So the higher that that sort of value is in the red tends to mean that you have more scattering materials, in the water as well. And then we have these waters kind of dominated by phytoplankton, which are characterized by this, the prominent peak in the green part of the spectrum. They're utilizing, a lot of blue light for photosynthesis here. This is chlorophyll absorption happening over here, and then these really clear offshore waters that we see. You'll notice the magnitude of those is a lot lower here. They're kind of dark blue offshore waters. They have low CDOM and low phytoplankton, so the photons essentially go deeper, and fewer are being scattered back. And you can see again, look at the red. It all disappears very quickly on these sort of waters. So that's why the spectra look generally darker overall. So I just like to look at these and kind of tell the story. You can just see the story of the water composition unfold just across all these spectra. So yeah, by looking at all these transect plots, you can kind of see how the optical properties, biology, water chemistry are all changing the light levels, leaving the ocean surface here. All right, now we intentionally highlighted this aspect of total spectral magnitude, that trapezoidal integration that we did earlier, because there's another important piece of information there that we don't want to overlook. As I mentioned, this AVW, it tells us about spectral shape, but it completely ignores overall brightness. It doesn't come into the equation here. So to isolate that total magnitude, let's do that calculation of the integration under the reflectance curve, using this sort of trapezoidal rule. This does take just a second here, because we're doing it to the entire image here. To run it. It takes less, maybe 30 seconds or less. But used together, it's a very useful aspect of being able to plot both the brightness and the AVW. So let's go ahead and plot them up both together. There we go. All right. These don't look the same. If you plot up most of your ocean color products, they're going to look roughly like this. Your chlorophyll, your IOPs generally follow this sort of pattern. Higher, closer to shore, lower offshore. Combining these is a really powerful diagnostic tool for really spotting interesting areas. For instance, you might see a region with high AVW but low brightness. This is kind of a random area here, right offshore here. Which it signals that the water might be rich in absorbing materials like dissolved organic matter versus brighter signals that you see from maybe sediments or clays. So this is looking at sort of the total integrated brightness, and then this metric of shape essentially. Similarly, offshore areas can relatively offshore areas, they can look kind of bright after sediment resuspension. Even if the spectral shape might look kind of, the same in normalized space, essentially. So I think it's really important that the information contained within the reflectance, both the shape and the magnitude, are giving complementary information that are not necessarily correlated with one another. I mentioned too that low brightness sometimes can highlight subtle features that the AVW alone misses, a potential bloom, maybe a deep water intrusion, or some other interesting phenomenon. You can't always exactly tell what's happening, but it sort of signal flags a location that might be worth investigating. Why is it so dark here, right in an area that's so green shifted, where you might expect brighter, more sediment driven waters to occur. So the key takeaway here is the reflectance. I know it's not an ecological unit in the traditional sense, but it is a direct window into what is going on in the water. And by looking at the full reflectance spectrum before any algorithms or indices transform it, we can see a really nuanced sign of change, and AVW and brightness kind of help us interpret. But the real story is in the spectra themselves. So there you have it. Hyperspectral RRS, maybe demystified for you. but I hope you can see that, how the tools here just make it a little more approachable and let you kind of get hands-on with the raw reflectances. Another approach, Sachi mentioned using, now that we have the reflectance in an array, X-array, we can take the second derivative, for instance, and hone in on a specific region and look at the second derivatives and say, whoa, we plotted this up and there's this really weird portion that just pops up. That's unique. Now let's take that whole second derivative array and plot just that one wavelength and see where it pops up in this image. Where is that lighting up? That sort of pattern, investigation is really the fun part of kind of exploring the power of the hyperspectral data here. But it is understandable that people kind of shy away from reflectance in favor of derived products, because something like chlorophyll A can feed directly into an ecosystem model, which is very useful, no doubt. But just remember that every step you kind of go away from this reflectance, it adds assumptions, uncertainty. So sometimes if you can stay closer to this sort of first form of data, you may possibly get better insights. But in fact, there was a study shown that using raw reflectance actually outperformed derived products in some contexts for modeling Atlantic sturgeon habitat along the East Coast as well. So they found the reflectance tended to work better. So it might be tempting to skip straight to indices, but I think the reflectance kind of gives you the richest, most nuanced view of what's happening in the water. All right. Anyways, if you enjoyed this and you like sort of exploring reflectance and the spectral tools we've been using, and I got your tail wagging, there is a follow-up tutorial kind of on Thursday, and it's all about optical water types. It takes a similar but different approach to kind of interacting with this full reflectance data as well, which should be complementary to this. So, all right. Let me know if you have any questions. How am I doing on time? I run over a little bit.